All right, for this section, we're going to be talking about Hamilton's rule. And Hamilton, if you remember or don't, was part of the group. Him and Zook came up with good gene hypothesis. He came up with the idea of what's called inclusive fitness. And on the left, on the bottom, you can see a equation that he came up with. And we're not going to really work with that equation, but I do want you to understand how it works. So his idea is individuals do things because of the number of offspring equivalents that are an individual rears, rescues, or otherwise supports through its behavior, regardless of where it came from. And that's why we have adoptions and things like that. But the idea behind this is you are going to only do things if, for one, it benefits you, and it has less than the cost. And then there's another factor that really is what we're going to talk about kind of next, is the relatedness. Is you're more apt to do something for somebody you're related to. And so on the right is an example of gray-crowned babblers, type of bird. And they are group nesters where the offspring from the year before typically will hang out and help. And what they found is if they remove all the helpers from a group, or all except for one from a group, what you will see is the number of fledglings, the ones that actually successfully get out of the nest, is pretty low. But in a control group where you don't take any of those away, it's quite a bit higher. So the question is, why would they help? Well, it's a brother and sister, so they are related. So that relatedness would be higher. All right, and just to show you some of the ideas behind this, we have squirrels and the Belding ground squirrels, another ground squirrel, and most of the squirrels will do this, and it's an altruistic behavior, which I do want you to know that word, altruistic. The idea is they give these alarm calls, and we'll talk about that term later in another chapter or another section. But what happens is they give an alarm call, and you see it doing it here on the left, and you can see the two on the right are taking attention to that. And the problem with alarm calls is when you make that alarm call, you are obviously warning everybody, hey, there's a predator, we need to do something, but you're also drawing attention to yourself. So that predator, especially if it's a hawk, now all of a sudden can key into you. So the question is, why would you do it? Why wouldn't you just sneak off and let one of the others get taken, and then there's more food for you? Well, the idea behind this is you're related. And so the question was, who makes the most calls? And it turns out the adult females. Because again, if this colony is theirs, they know that these offspring are all theirs, or their sisters, or so there's some high relatedness. Now the males, on the other hand, if you look at the adult males, they're not very likely to call. And the reason is, I'm not sure all these kids are mine. I don't know if you've been cheating on me. And so they will do it, but it is a lot rarer. So if you notice on the females, as they get older, they tend to call more. And the males stay pretty much the same. Matter of fact, it's a younger male that is maybe more likely to call just because they haven't learned to shut up yet. Interesting. But again, it's this inclusive fitness. Who am I related to? Barn swallows typically the same way. And what you will see is very typical behavior is the offspring will help feed last year's, and again, when it comes to brothers and sisters, you share about half your genes. You share 50%, and so again, that is where it would be likely to do. And so what we're going to do, and I'm going to also do this in class, I think, because it's kind of a generation a little more difficult on understanding, is kind of how do you do these little relationships. And so this is kind of a chart if you wanted to kind of do the math on, who's related to who. So you can go through here and kind of look, and it can get a little bit confusing. But if you get a pedigree like this is how you kind of figure it out. We're going to start with B. Well, we'll start with A, I guess. We'll start up here. And so what you do is you go down and figure out, how closely related you are to each other. So here I've got the circles are female. So here I got grandma, and grandma, yeah, she's hanging, she's sleeping around a little bit. She's got two males here. So I've got a, X and Y. We got a brother and, we've got, I'm not even sure they're brother and sisters, but we've got these kids, okay, grandkids. We want to know how closely related they are. What is their R? What is their coefficient? And so what you do is you go down, and this male here is going to share half the gene. So that's a 0.5. Okay. And then you go down here, and how much is, so it's going to be half of a half. So that's 0.25. And then you do the same thing on the other side. So it's a 0.25. And then what you do is you multiply 0.25 and 0.25. And if you do the math, you get 0.0625. And that's how they're related. Now it's a little bit here. You notice the number has changed to 0.125. And that's because here they're sharing both of the kids. Not kids. That's weird. Both of the grandparents. So again, the math is kind of the same. I got a 0.5 here and a 0.5, and then I got a 0.5. So that goes down to 0.25. I multiply those together. But because I've done it twice now, because I have both relationships, I got to multiply it by 2. And that's where you get this. And you can now do this for different generations. So here I've got a 0.5 and a 0.5. Multiply those together. It's 0.25. But then if I go here, I've got a 0.5. Here I got a 0.25, or 0.5 times 0.25. I get 0.125. So what I'm trying to tell you, hopefully that makes sense and you kind of work through it, is that I'm going to do one of these for the test. And so I want you to be able to calculate these. But we're going to make sure, and we're going to go through this to make sure that you kind of understand it. So we'll do this also in our Zoom session. In that, will be